In the realm of high-speed mechanics, acceleration is optional. Stopping is mandatory. When a vehicle brakes hard from 60 miles per hour, physics takes a violent turn. Pads clamp down on the spinning rotor. The screech of friction deepens into a low thermal groan as the metal fights the momentum. In mere seconds, kinetic energy vanishes, replaced by a blast of heat reaching 1,000 degrees Fahrenheit. The steel glows a vibrant, dangerous red. This is the temperature of magma inside an active volcano, yet the disc must hold its shape. Billions of these components are forged every year to tame billions of tons of moving metal. But what material can endure this repeated thermal shock without shattering? The journey of a precision brake disc does not begin in a high-tech lab. It starts in a pile of garbage. Many of these critical safety devices are simply resurrected scrap. Precision engineering meets the graveyard of industry. Before a brake disc stops a supercar, it likely lived a different life as a washing machine or a structural beam. In these yards, electromagnets humming with high voltage hoist thousands of pounds of ferromagnetic waste in a single lift. But sorting is not enough. The metal needs to be erased. The scrap enters the maw of a mega shredder where the process turns brutal. Inside, massive rotating shafts armed with free-swinging steel hammers spin at blurring speeds. The sound is a continuous, deafening car crash. These hammers strike with enough force to shatter engine blocks, processing dozens of tons of material every hour. What was once a distinct object is annihilated. The rotating hammers pulverize solid beams into a flowing river of jagged fragments. Crushing delivered the necessary physical size, but chemically, this stream is still a hazardous cocktail. To forge high-performance steel, the raw material must be surgically pure. The conveyor moves the debris under a massive drum magnet. Ferrous steel leaps upward against gravity, clinging to the belt, while heavy rubber and glass simply drop away. But copper and aluminum are the enemies of structural integrity. They require a different force. An eddy current separator waits at the end of the line. A magnetic rotor inside the drum spins at 3,000 revolutions per minute. This induces a current in conductive non-ferrous metals. They are not attracted, they are violently repelled. Copper wiring and aluminum shards are ejected from the stream like popcorn. Finally, optical sensors and X-ray eyes scan the flow for the last traces of contamination. High-speed air jets blast away stray plastic with millisecond precision. The chaotic river of garbage has vanished. In its place is a uniform, glittering stream of shredded scrap with 99% purity. This is no longer waste. It is a calibrated charge waiting for the furnace. Cold, jagged shards are dumped into the belly of the electric arc furnace to meet a man-made electrical storm. The massive steel roof swings shut, sealing the chamber in darkness. 3 graphite electrodes, each the thickness of a telephone pole, descend through the lid and stop inches above the scrap pile. Then, the circuit closes. A blinding flash ionizes the air. A deafening crackle explodes as arcs of plasma strike the metal, converting electricity directly into thermal violence. The sound is a physical force, a continuous thunderclap trapped in a steel box. The temperature at the tip of the arc rockets to 3,000 degrees Fahrenheit. This is hotter than fresh volcanic lava. The steel liquefies instantly. Supersonic oxygen jets blast into the boiling bath, burning off carbon and churning the mix like water in a kettle. Impurities are trapped in a floating layer of slag, leaving the iron beneath chemically pure. 100 tons of solid waste have vanished. The electrodes retract and the roar cuts out, leaving only a quiet, glowing pool of liquid fire. Liquid steel is chaos. To become useful, it must find a permanent shape without losing its strength. The melt pours into a ladle, a massive refractory-lined vessel holding dozens of tons at 2,700 degrees Fahrenheit. This is hotter than the re-entry heat of a space shuttle. Engineers immediately inject aluminum or silicon. These elements hunt down dissolved oxygen. If they fail, microscopic gas bubbles remain trapped, turning the metal into a sponge instead of a shield. Now comes the phase shift. The molten stream flows into a water-cooled copper mold. As liquid steel hits the chilled walls, the outer skin freezes instantly. A solid shell forms in milliseconds, but inside, the core remains a raging liquid. Rollers pull this strand downward at a precise speed, while high-pressure water sprays blast the surface. The temperature gradient is extreme. The surface is solid, while the center is hundreds of degrees hotter. This controlled cooling forces the crystal lattice to align perfectly, preventing internal cracks or porosity. The continuous red-hot bars slide out of the caster, ready for the next assault. The raw castings look solid, but deep inside, invisible forces are tearing them apart. Rapid cooling has created dangerous residual stresses within the iron structure. To fix this, the discs travel through a long tunnel furnace. Temperatures climb to 1,200 degrees Fahrenheit. That is nearly half the melting point of the metal itself. The air inside the chamber vibrates with heat haze. Nothing moves on the surface, but at the atomic level, the rigid crystal lattice begins to relax. The iron atoms, locked in tension, vibrate and realign into a balanced formation. This process is critical. Without this thermal bath, the internal tension acts like a coiled spring waiting to snap. The first time a driver hits the brakes, that stored energy would release. The disc would warp or crack under the pressure. The furnace slowly lowers the temperature to lock the new alignment in place. The molecular structure is now fully stabilized. The molecular chaos is tamed, but the physical form still needs discipline. The cast blank arrives covered in a rough, oxidized crust. It looks more like an ancient relic than a modern car part. The disc is clamped into a computer numerical control lathe. The spindle roars to life. Ultra-hard carbide cutters engage the surface. The high-pitched scream of metal shearing off metal fills the chamber. This is not brute force. It is surgical removal. The tools shave off layers thinner than a sheet of paper to reveal the clean steel beneath. The goal is absolute parallelism between the two friction faces. The margin for error is almost non-existent, 1 to 2/1000ths of an inch. That is finer than the width of a single human hair. Drills pierce the central hub for mounting bolts. The transformation is total. A jagged lump of iron has become a mirror-smooth instrument of control. Perfect geometry is mandatory. Any imbalance here would translate into catastrophic vibration when the wheel is spinning at 2,000 revolutions per minute. The brake disc is designed to generate friction. It exists to convert kinetic energy into searing heat. But before deployment, the raw metal requires a shield. A layer of anti-corrosion oil, thinner than a fingerprint, seals the surface against moisture during global transport. The disc acts to kill motion. Its mechanical opposite acts to preserve it. The ball bearing. This is the industrial antagonist of friction. From automotive hubs to aerospace turbines, billions of these steel spheres are produced annually to keep the world rotating efficiently. But creating a perfect sphere starts long before the grinder. Where does the metal for such flawless geometry originate? To find the source, we leave the clean assembly line and descend into the open pit. To forge pristine steel without a single scrap of recycled metal, we must crack the planet's crust. We leave the sterile, micron-perfect assembly line for the brutal scale of the open pit. Here, precision is not measured in millimeters, but in megatons. Drills bore 50-foot shafts into the bedrock to plant the payload. The chemistry is simple, but devastating. Ammonium nitrate mixed with diesel fuel. The fuse is lit. Detonation. A ripple of blasts, timed to the millisecond, liquefies the geology. The shockwave hits the chest before the sound reaches the ears. In a heartbeat, thousands of cubic yards of solid cliff shatter into gravel. Through the haze, the giants awake. Hydraulic excavators swing buckets holding 40 tons of ore, enough weight to crush 10 passenger cars flat in a single scoop. They feed dump trucks weighing up to 300 tons. In the vastness of the crater, these mechanical beasts look like die-cast toys, yet their tires alone stand 12 feet high. One mine consumes over 1,000 tons of explosives every month just to feed the furnaces. The roar of the diesel engines fades. The heavy dust begins to settle. But massive boulders are useless to a chemist. To extract the metal, the rock must be erased. The raw ore is fed into ball mills, rotating steel drums filled with heavy grinding spheres. The impact is relentless. The stone is pulverized into a dust finer than flour, maximizing its surface area for the separation phase. Then comes flotation. The powder mixes with water into a thick sludge, and reagents are added to alter the physics of the material. The iron particles become hydrophobic. They repel water. The silica and clay impurities remain hydrophilic. When compressed air blasts through the tank, millions of bubbles rush upward. The iron particles latch onto the air pockets, riding them to the surface like microscopic life rafts. A thick reddish-gray froth rises to the top. This foam is skimmed and dried, leaving behind a concentrate that is 65 to 67% pure iron. The inert stone is gone, and the dark powder is now ready to enter the furnace. This is the most aggressive stage of the entire operation. Chemical reduction. The dark powder does not simply melt, it gets torn apart at the atomic level. Inside the vertical steel stack, the charge enters in precise alternating layers. Ore, coke, limestone. Then comes the blast. Preheated air screams into the base with the force of a hurricane. The temperature spikes to 3,600 degrees Fahrenheit. This heat triggers a chain reaction. The burning coke releases waves of carbon monoxide gas that race upward through the stack. This gas acts as a chemical thief. It strips oxygen atoms away from the iron ore, forcing the gray rock structure to collapse. Gravity takes over. The solid layers vanish, replaced by a river of liquid fire. Heavier molten iron sinks to the bottom of the hearth, glowing a blinding yellow-white. Above it, impurities bond with the limestone to form slag, a molten waste floating on the metal like oil on water. This efficiency comes at a staggering cost. For every ton of steel produced here, the blast furnace releases nearly 2 tons of carbon dioxide into the atmosphere. Molten iron flowing from the blast furnace is heavy but chemically weak. It is too brittle for modern engineering, requiring a violent oxygen attack to survive. The stream transfers into the basic oxygen furnace, a massive vessel shielded by heat-resistant refractory bricks. Here, the process shifts from simple melting to high-velocity physics. A water-cooled lance descends into the vessel, stopping just feet above the churning surface. It unleashes a jet of pure oxygen traveling at supersonic speeds, faster than a fighter jet. This gas strikes the liquid metal at twice the speed of sound, igniting a ferocious chemical storm. The oxygen aggressively binds with carbon impurities, generating an exothermic reaction so intense it sends flames shooting out of the furnace mouth. No external fuel is needed, the heat comes from the burn itself. As carbon evaporates, the metal loses its fragility. It transforms into refined steel, capable of bending without breaking. The liquid mass is now compliant and ready to take its permanent form. Before the blast furnaces of the future timeline can ignite, the raw earth must survive a preliminary hell. The material enters a rotary kiln, a steel tunnel angled for gravity flow. Inside, the atmosphere stabilizes between 2,190 and 2,460 degrees Fahrenheit. This is the sintering zone. The heat is calibrated to incinerate impurities but stop just short of liquefaction. The iron particles do not melt, they fuse. As the drum slowly turns, the pellets tumble through a uniform thermal soak, bonding at the atomic level into a dense solid mass. The dust becomes rock. They emerge purified and hardened, glowing at an exit temperature of 2,000 degrees. Just as with the pellet firing, temperature here changes the molecular structure, but this time the goal is precise formation. How do you create a heavy industrial ring without a single weld to weaken it? The steel blanks first undergo a controlled cool to banish residual stress. Then they return to the heat. Inside the furnace, the alloy becomes ductile. It is ready to yield. The automated ring roller takes over. A mandrel inserts into the center of the glowing blank. A driver roll crushes it from the outside. The pressure equals the weight of a blue whale pressing down on a dinner plate. The metal flows. The wall thickness shrinks as the diameter expands. This is plastic deformation. The grain of the steel stretches around the circumference, creating a continuous, seamless loop. Sensors catch microscopic deviations. Any excess edge material is sheared away instantly. The ring enters the final heat treatment cycle to freeze this geometry. Hardness spikes. The heat leaves the metal. Silence. Before facing the crushing mechanics of the rolling line, the steel must lock into a solid state. The molten stream dives into the continuous casting machine, flowing directly into water-cooled copper molds. The thermal shock is instant. The outer skin freezes in milliseconds, trapping the still liquid core inside a hardening shell. This is a critical phase transition. The chaotic fluid structure aligns into a crystalline lattice, emerging as an endless glowing strand. These strands are sliced into massive rectangular slabs or square billets, but the shaping is not over. The steel is immediately reheated and fed into the rolling mills. The force applied here is geological. The metal is compressed between giant cylinders weighing over 50 tons. That is the equivalent of a main battle tank, spinning and crushing the red-hot slab into a thin sheet. Flattened and extended, the steel accelerates down the conveyor, racing toward its final transformation. Those massive steel slabs begin existence as a microscopic wet suspension. Inside the vacuum disc filters, a high-pressure differential violently separates the valuable ore from the water. The liquid is sucked through a fine mesh, leaving behind a dense, sticky residue known in the industry as filter cake. It feels like heavy wet clay, but it quickly dries into a fine, volatile dust. You cannot feed this loose powder directly into a blast furnace. It would choke the airflow instantly. To create structure, the dust is mixed with organic binding agents and fed onto massive inclined pelletizing discs. These saucers rotate at a specific angle, using gravity and centrifugal force to roll the particles over themselves in a continuous cascade. It is the snowball effect miniaturized. From chaotic mud to geometric order, what entered as sludge exits as millions of perfectly uniform spheres, chemically prepared for the kiln. The formed steel now requires surgical cutting. Solid bars of high-carbon alloy, fortified with chromium for extreme wear resistance, enter the fabrication line. Verification of the steel grade is instantaneous, but the physical separation requires brute force controlled by light. Laser sensors scan the metal surface, positioning the bar with microscopic precision before the clamps lock. Then the hydraulics engage. A blade driven by hundreds of tons of pressure slams down. It shears through the cold metal in a fraction of a second. The result is a short cylindrical blank, the raw canvas for the future bearing. Speed is constant, but accuracy is paramount. Automated scales weigh every single slug that drops from the blade to ensure the volume is exact for the forging dies. The machine enforces a strict weight tolerance of plus or minus 2 grams. After the rough cutting and massive pressure of rolling, the process shifts gears. Now begins the fight for microns. Computer-controlled lathes engage the cooled steel, using ultra-hard alloy cutters to shave the outer dimensions. They lock the diameter and thickness into place, but the most critical feature requires abrasion, not cutting. A precision grinder carves the raceway directly into the ring surface. This channel is the track where the rolling elements will eventually travel. It determines the lifespan of the entire mechanism. To achieve a flawless finish, the rings enter a blast chamber. High-pressure nozzles unleash a torrent of steel media against the metal. Millions of fine shots strike the surface every second. This bombardment strips away stubborn oxide layers and obliterates microscopic burrs that no blade could catch. The impact compresses the steel skin, creating a uniform texture capable of withstanding extreme stress. The pristine rings slide onto the conveyor for the final merger. Polished rings are useless without correct assembly geometry, but the rings are solid steel. No seams, no welds. How do the balls get inside? The solution is eccentric displacement. The machine forces the inner ring off-center, opening a temporary crescent gap just wide enough for entry. Steel spheres dive through the void and fill the raceway. Gravity feeds them in. The assembly rotates and the rings snap back to a concentric state. The balls are trapped in a micron-perfect orbit. Now they must be tamed. A separator cage locks onto the rolling elements to prevent clustering. Click! The sharp sound of mechanical alignment. A final dose of synthetic lubricant coats the track. The process is complete. Friction is dead. The steel spins. Zero vibration, absolute silence.